All right. Will somebody ask me if I'm excited to be here today? Beddington, my guy. All right. So I just wanted that because I heard somebody say it this morning. Okay. From the other day, we were looking at conservation of momentum, and this is what it's always going to look like. Now, today we're going to expand this idea if we lecture. I'm leaning toward lecturing today. I know that might not be what you love, but I'd rather have 2 groups, not have people, than 4 groups if we go out there. But we'll have that time to decide. Okay. This is a video that we worked the problem that we worked the other day in class, and this is different because I did it up on the board, but I wanted to draw everybody's attention to this, and I did draw everybody's attention to this when we did this first example problem, because when we look at number 18, and I know it's weird that it's called 18, this is because it's 18 out of your textbook, just so you know. When we look at it, we have a goalie at rest, he's B, and a puck is shooting at him. Much like a freight car at rest and another one hitting it. Like same situation. So I list out all the knowns, and I imagine you guys get the same thing, and check it out. As soon as I realized one of them was at rest and I've already done this problem, I know that I can use this formula. Exact same formula. I can work it out all the same. I would start here, I would expand out to this, and I would solve for this. Okay, exact same thing, which means I can just blindly bless you. Not blindly bless you. Speaking of, well, wait. Okay, looking at this, just plug and chug. I put in all the values. Did you guys get 0.34 meters per second? So I'm going to take off my half credit here. Okay, not our focus whatsoever, but did y'all hear about Francis? Yeah. Yep. It is crazy. Popes live for a long time. This is the 4th pope that I've seen. Like, I'm going to have seen 4 popes in my life, which is pretty crazy. You guys are at probably 3. John Paul, Constantine, Francis, and now there's another one coming. No idea.
I saw Pope Francis speak in Italy.
Cool. That's a good point. All right. So, looking at number 19, we see something similar. I'm just going to let you guys check it. This bullet is ungodly fast. 1237.17. Meters per second. Okay, just so that you guys are aware, this is not a realistic bullet unless we're shooting it out of like a rail gun. Does not go this fast. Regular, like even fancy, like hunting bullets that you might use, they're going to be like the 1,200 to 1,400 feet per second, not meters. This is 3 times faster than a regular bullet. Crazy fast. Okay, 19, yay, nay. Cool, cool. Okay. Was 20 harder? I don't know. Did you get 2.8 meters per second? Cool. Sean, do we have a difference?
I think I accidentally multiplied decimal point.
So you did 0.35?
Yeah.
Okay. Did you just get the same answer but 28? Okay, that'll do it. All right. And 22. Any harder? Okay. 22 meters per second. I hope. Can't get a read on you guys. Am I wrong? So no affirmation. Riley, what'd you get? Okay, so that's okay. I could be wrong. I did this at home randomly with a child, I imagine, screaming at me or near me. What'd you get?
-2.
-2. -2. So let's see here. Let's see if we can find my mistake then. Okay, we have a 0.5 kilogram ball traveling at 6 meters per second. Cool. And a 1 kilogram ball going the opposite. Hey, I found my mistake. What should this be? This should be negative. Got me good. -2 is an okay answer? All right, I'll take it. -1 for Holloway. Cool. All right. Thumbs up, thumbs down. Yo. Again? You're killing me, Sean. Thumbs up, thumbs down. How'd it go? Okay. Let's check out the next three, and then I'll take both of these, okay? Baller. Okay, so the next ones, and I'm going to have to cross-reference. And you left it at home, Nick?
My cat peed on it.
What's that?
My cat peed on it.
I will get you a new one. I don't want that one.
My cat's been peeing everywhere.
Is it in heat?
I don't like that.
I don't know. Lately, we've let it out outside. It's been an outside cat, and it was potty trained when we got it, right? But then lately, it's been just peeing everywhere. Like on my birthday, we woke up, she started peeing in the laundry. My mom picks her up, and she just continues to pee in the air.
Oh my god, please what she's
Well, that's unpleasant.
Yeah. Well, my cat's
All right.
getting excited.
So, let's check them. And apparently I did the wrong problem set, but that's okay. Okay. We are doing 4 kilogram model rocket. Does that sound like the right problem to you? I don't know if you guys wrote it down or not.
Yes.
Holy cow.
Yeah.
Okay, so we're in 9.2. Sorry about the issue here. I don't know how I did the wrong problems. 4 kilogram model rocket. 7.9 meters per second in the end. On number 19 from, whoa, just kidding, it's number what? 23. We are shooting for 7.9 meters per second. Okay, on 24 we have a thread connecting a cart and a cart. So let me find that one here. 9 centimeters per second. Ooh, you probably don't have centimeters per second. Do you have 0.09 meters per second? Okay, I'll take it. 0.09 meters per second. Okay, so if we need to check that one, we can. Looking at it, and I'm just going to show you. I don't always do stuff exactly like they do. A lot of them, they use funny letters and stuff. But let's check. You start with conservation. Initial equals final. And then they're both 0. Okay. And then we just plug in these values. The final velocity or final momentum equals opposite of the initial momentum. Cool. We plug in and we solve. And I'm guessing that this could be it. You might have 0.27 meters per second here.
Yeah.
Oh yeah.
Okay, that's where it happens. Okay, easy to fix. All right, number 21, together or what'd you guys get for answers?
21.
Just kidding. Gosh, my numbers are very different. 25. This is what Carmen and Judy, I think.
2.795.
2.795 meters per second. Opposite direction. 2.8 is what this has, meters per second, opposite direction. Okay, so today we're going to get a little tricky. I have come to the conclusion we're going to do a short lecture. I don't know that I'm going to give, it's not going to be super long, but we will intend to go out to the wood shop tomorrow. Okay, I know that totally, I'm sorry you won't be here. We will go again next week. We're going to keep going. Awesome. All right, so we'll pause this for a moment. That's not the video, right? So, welcome back, physicists. Today, this is where we're looking at. Yesterday, we looked at propulsion. So, Nick, what you missed yesterday is this idea of recoil. And it's naturally, we have a good sense of this. If you and I, let's say you and your little sister are both standing on rollerblades, and they're perfectly oiled, there's no friction. And you're both standing still, and you push her. Does she move? Do you move? Okay, so that's recoil. Boom. Yesterday, we looked at it with this, not that. We looked at it with this example, and I can see that, hey, look, this person's moved back a little bit, this person's moved forward more, and even all that force is generated within, so there's no issues with conservation. And then it turns out that this is the exact same idea that leads to an astronaut with a jetpack. Firing hot gas is the example that we used yesterday to get back to the ship. So whether it's firing that or if I throw something, I also get recoil out of the deal. Same idea. Okay, today we are bumping it up a little bit. And I'm going to awkwardly just get a new one. Get out of here. Cool. Nope, cancel that. Eventually this is going to crash and it's going to break my heart. All right. So, for today, we're continuing on. We are still in conservation of momentum stuff, and we're coming near the end of the section. Be prepared to draw some circles here for a second. How much money you got? Did everybody give them back the other day? I don't think so. Some of you still have the circle drawers, right? Cool. Yep, circle drawers. We really don't have that many. But for the first time this year, second time this year rather, drawing pictures is going to be so important to help us make sense of stuff. Okay. Other weird thing for like 90% of you. Pre-calc overlap is insane today. So same ideas, it's nice, the math works out the same. We just get to see how do we apply the math that we're literally doing right now, which is pretty cool. All right, so for today, we are jumping ahead, and we were looking at collisions, right, and how momentum plays into that. And we saw that momentum is conserved before and after, and we were looking at collisions in one dimension. That's all we were doing yesterday. Now, whether they're both straight, to the right, or up, or it doesn't matter, one dimension. But what's cooler than one dimension collisions? That is in fact correct. It is two-dimensional collisions. Two-dimensional collisions. So conservation momentum is still going to apply, but we're going to have to think about it a little tiny bit differently. So two-dimensional collisions. Now, for this, I'm going to use a quick picture for us to make sense of this. Okay, let's say that we have a ball here, and it's ball C. Cool. And ball C is going to be, it's like a billiards ball. Let's say that ball C is going to launch at another ball here in just a second, and we'll say that that second ball is ball D right here. So notice it's a little bit off. They're not level, because just so you can draw it accordingly, when these hit, let's say that this happened, you don't have to draw these arrows yet. What way is the D ball going to go? So can you give me a direction on the board? Yeah. When it's just going to go straight like this. So notice the askew part. It's going to go like that.
Oh.
And then C will then go kind of that way. Everybody agree with that? Like if you've ever played pool, you can see this. Now, I think that I like this method. It's not what your book does, but I love it. Eventually, if we give this one some initial momentum, so we'll say, check it out, here's the initial momentum of C, I'm sorry. So it's moving, that's what we know. And D is at rest. Eventually, these guys are going to collide. And we'll do it here. And I'm going to draw it like this and say, check it out, there's C colliding. So we don't have to do before and after, truly. And then we know that D is going to move down this direction. And I don't know exactly the angle because we weren't told anything about it. But I think that this is going to be the momentum of D after the collision. Which, how would I indicate that? Rho D what after the collision? Final, love it. Okay, and then C is also going to come up this way, I would assume. Following the collision, we'll have rho of C final. And C will wind up somewhere up here. And I will try to stay, whoa, that's D down there. I'll try to stay consistent, but I like the dashed circle to indicate that this is the moment of collision and then after the fact. Okay, from this, I want us to think about what's going on here. Now, I know that momentum must be conserved, but there's something bigger at play here. Right now, instead of just working in the X dimension or just the Y dimension, we're in X and Y. There's some horizontal movement and some vertical movement, right? So as we look at this, what we are going to think about, and we're going to try to break it down for somebody who maybe hasn't seen vector stuff this year, this problem is exactly the same, but now we have two dimensions. We do the same thing with one little tweak. We do the same as before, so the same conservation stuff is going to apply, with one little exception. If you give me a diagonal line, there are an X piece and a Y piece, right? Those are called the, it's a form of a vector that you might have talked about yesterday. Louder? That wasn't any louder, but I like it. They are my components. Okay, we do the same thing as we were doing yesterday and the day before with conservation, but consider our components. And I'm just going to say, but with components. Now, I've said that word like 30 times and I'm afraid it's losing meaning. All this means is X part, or piece, the component is the real word, and a Y piece. There are two separate pieces that need to come together, X and Y. Now, as we look at this, there's a few ways that we can think about it, and I don't want to say like here's 10 different ways to do it, but I do want to make sure that you're aware of how we can connect these kind of thought processes. So, right off the bat, I know that if you were to take the initial momentum of C plus the initial momentum of D, what would that have to equal? The final momentum of C plus the final momentum of D. This is nothing new. What is this called? So that's a good thought. Not standard form. You're thinking pre-calc, and that's okay. I get it. Conservation of momentum. All right. Now, for this, I made the comments already, and I've kind of given you the answer. But after these things collide, I have components, right? There's some motion that goes in the horizontal direction, and there's some motion that winds up going in the vertical direction, right? We have to deal with these separately, which means we might take this, and I'm going to use different colors just to really highlight the difference here. This thing could lead to the X dimension, which, if we wanted to, we can make sense of this and say, check it out. PCI, or the initial momentum in the X direction, and I'm going to write 0 for the next one, and I want you guys to tell me why. Why is there no initial momentum in the X direction for the second ball? For ball D. And I'll write it, but I'm going to cross it out. So DI in the X direction. Why is that 0? It's at rest. And I didn't write that anywhere here, so you might not have seen that or caught it, but we're hitting a pool ball that's at rest. Okay, this should be equal to the final momentum of C in the X direction plus the final momentum of D in the X direction. Now, as we look at this, it can be hard to pick out, but all we're seeing is, check it out, this thing has X here, this has X right there, and this has X right here. If we add up these two X's, they better be the same as this one. That's all that we're saying. Okay, I'm not going to make this drawing awful with all those little marks, but I want to connect it. Can we do something similar for the Y direction? Gosh dang it, yes, no questions. Okay, let me change that again. I want you guys to do the same thing for the Y direction, noting if there's any zeros that are worth mentioning. I'm going to give you a second. But if we write it all out, I know that I get the initial momentum of C in the Y direction plus the initial momentum of D in the Y direction. That is equal to the final momentum of C in the Y direction. And this is kind of redundant, but we're going to get there. You guys came up with something similar, I think. Now, there's more to it, to this picture that we're going to talk about. We don't need to do the full problem. If you trust my drawing, which you can, what's the initial Y momentum of this guy? That would be 0. And what's the initial Y momentum of this ball that's not moving? 0. So what we wind up with is that these two have to be exactly equal but opposite. Okay. Conceptually, graphically, with vectors, what that means is that if I were to draw the Y component of C final right here and the Y component of D final right here, what do you think those two do with each other? They cancel. They zero out, and that's super convenient when it happens. Okay, one more big comment that I need to make before we do a problem. When dealing with these types of problems, pictures, pictures, pictures. They don't have to be perfect, but you should draw a sketch. In these two dimensions that we're working with, I'm going to put a star because it's such a big helpful thing. In 2 dimensions, which I'm just going to call 2D. In 2-dimension situations, we will construct a triangle with legs, and I'm going to say two sides because they won't always be right triangles. Rho I x, or rho x, I'm just going to say, whether it's initial or final will depend on the problem. Rho y and rho final. Okay. The pictures are going to be super important to help us make sense of stuff. I cannot stress it enough. All right. So what I want to do then is we're going to work through a problem. And if you want to read it in your text, you can. I'll put a picture of it up on here. But we're going to do an example or two together. And then you guys will have like 10 or 15 minutes, I imagine, to work on stuff. Or if we don't, I will not give you new homework because this stuff takes practice. Cool. Okay. We will have to work with the components to get the final momentum. That's the goal. Okay, so let's do a problem. If you don't want to write down the whole problem, which I'm totally good with, this is example 5 that you will find waiting on page 250. And I will pause it and I'll get the picture up here so you don't have to write down the whole paragraph. Here is example 5 on page 250. Okay. So we're going to try to draw a picture first, and then we'll list out our knowns and stuff. And we might have to refine our picture and make it better later, but let's check. We have a car labeled C that moves north at 27 meters per second. So there's a car with a mass and a velocity. Does it have a momentum? Okay, so we have momentum of C initially. And it's going to hit and collide with a heavier car D that's moving east at 11 meters per second. Now, I don't know these values off the top of my head, but I do know that the collision caused the two cars to stick together. We're trying to figure out what's happening. Now, we're going to see this really cleared up today in pre-calc, but if I wanted to draw little vectors to represent this situation, all I'm doing is I'm reading through and saying, okay, it has to go north, and then it goes east. So there's my jumping in point. Here's one car's momentum. And if it's traveling due north like this, this is the momentum, PCI, sorry, which car? Gosh dang it. Okay, it was C. Okay, here's my initial C momentum. And then remind me, it's been a long time since we had to do this, but if I go da, 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 does that stir any physics memories? What is it? Tip to tail. So check it out. I have car C moving north, and we'll find this value. It's going to collide with car D that's moving east. And off, just total guess, can you tell me which one you think has more momentum? 1325 at 27 or 2165 at 11? I think so. I'm not 100% sure. Why? So this is more than twice as big as the other one. Yeah, I agree with you. Okay. I don't care about the actual values. The picture's just going to be close. This is the initial momentum of car D. Now, that's going east, isn't it?
Yeah, but they fly.
Yep, so we're going to see it. We're going to see it happen right now. Okay. Now, for this,
So it's going to T-bone.
it's like it's T-bone. Yep. Okay. This is where things get a little bit strange and really important. Our triangles are going to be helpful. This is due north, due east. If these cars collide, which way would they go? Northeast, do you agree with it? It's almost like they would go in this direction. Like if we just add these vectors together, right? Okay. This is the importance of drawing this triangle. As soon as I draw this triangle, can you tell me what idea from math you think we're probably going to use to solve it? Oh, Pythagoras is going to hook it up. So, we have this picture sorted out. Let's run through it now that we have it and see if we can't make sense of stuff. So, I will switch colors to indicate that this is just where we're starting. Can somebody tell me something I know? Nick, give me one thing I know. So I'm going to change that number, but I like your idea. 1,325 kilograms. Okay. Does it feel more natural to do the velocity of C next or the mass of D? Do you guys have a preference? I go back and forth. Mine has both masses together and both velocities together. So let's do this. The mass of D is what, 2165? All right. What else do I know? Fern, give me something else.
RC is moving north at 47 meters per second.
Which measurement did you just give me?
Velocity of C.
There's one more little piece you're missing.
Velocity of C.
So I'm going to say initial first, but you're right. It is in the Y. Okay. All right. And what about the velocity of D, Huggins, initially? Okay. 11.0 meters per second. And I like to include north, east, south, west because it doesn't make sense to say this is positive and this is positive when they're going perpendicular. Like we know it is positive, but it's because 2 dimensions. So I'm going to include east. Okay. That's everything that I know, I believe, right? Cool. What am I trying to find? In what direction and with what speed do they move after the collision? So that's really just asking for the final velocity. And, gosh, direction? So this is going to be hidden within the final momentum, but I like that idea. How do we measure direction? You could use a bearing, which is just an angle, right? Okay, so we need theta final as well. Now, as we look at this, there's some stuff that we are going to see mixing back and forth with pre-calc, and I don't want you to have to be in pre-calc to be able to be successful with these, so if this is a little slow for pre-calc, sorry, not my intent, but it might be a little different than pre-calc as well. Okay, so here we are, we're starting this problem, totally this is page 250, if you want to read, like here's the whole problem, it's just tiny on my screen. But there it is, and we're trying to find both of them. So let's dig in here. If I want the final momentum, just thinking about this picture, we know that we have to use Pythagorean theorem. Everybody cool with that? Okay, so there's a few different things that we could start out with if we wanted to. If I wanted to work in just the x direction with both of them, I can. And we're going to sneak in some old ideas here with this. If you give me this vector, c in the original direction, this is a magnitude, right? Could you tell me the angle that it's traveling at? So let me rephrase that. Tell me what you view. If I said, hey, what angle is car C traveling at initially? I want to know what you come up with. Chat it out. I don't think you're going to be wrong, but if you are, it's not a big deal. What direction are cars C and D traveling in? Rather than north, can you give me an angle? Huggins claims 90 and 0. Can somebody second that? Why 90? Yeah, it's perpendicular, and you should not draw this, but remember, we work on a coordinate system where we always measure angles like this, counterclockwise. It's 90 degrees. Now, depending on how pre-calcy you want to be with it, I'm going to throw in a couple little recall things here. Recall. Given, if I give you a magnitude or a radius, which we can think of as radius. If I give you a radius and an angle, we have a few different little pieces. So we'll say radius r, and an angle will just indicate theta. There's some really handy stuff that we can use here. Okay, if we elect to not do the problem this way, that's okay. This is the most efficient way through it, but it isn't the only way. If I give you this, we could find direction and magnitude of the components pretty easily. If I want to know that this is, if I know that this is 90 degrees, like you guys just told me, then we could work this out. I know that in the initial momentum in the x direction for C is going to be equal to r times some trig function. And if I want the x direction, am I going to use cosine or am I going to use sine? Which one is x? Cosine is x. We have this idea, r cos theta. Okay, anybody who's looking at that, imagine that we have a lovely circle around this. You don't have to draw it, but if here's a circle, if this is my radius, I have the radius r, and the cosine of theta gives me the x value. Okay. We'll undo that. Now, in this situation, it works out, and it's obvious, I think, once we look at it. If a car is going due north, what is its x momentum? Or x velocity even? It's 0, because it's not going left or right, yeah? And if we check this just against it, we could see that the radius is whatever mass of c times velocity of c is. So I'm just going to write this out. Mass of c, velocity of c. This is like my radius r in this situation. Times the cosine of, what was that angle again? 90 degrees. And can everybody point to 90 degrees for me real quick? And what's the x coordinate right up here? 0. It's 0, comma 1, right? So this is 0, which means we just mathematically verified what I think was obvious. It was 0 to begin with. Don't even care what the momentum is. Everybody cool with that? Okay. What are we going to get? I don't think I want to show it all. But if I wanted to do the same thing with D initially, but get the x and y components, it's all x or all y component on vector D. So on this one up here, Tully. Oh, spit, he says. It's all x, right? So if I use the sine of 0, I'm still going to get the 0 out of it using r sine whatever. Okay. This technique and this approach to getting components is super helpful, and it can be. Now, if you don't want to take the super mathy route on problems where we already get 90 degrees, we have another way through this. Does everybody have this written down if you want it? Okay, I'm going to clear it here. Okay, so check it out. If we want, and we've sketched and we realize that we have a lovely right triangle already, could you find me this? I'd love it. Can you guys still see that if it's that fine? I saw somebody's face indicate maybe not perfectly. All right, so if we wanted to find, I don't know, this, which I know is all in the x direction, could you guys find it? Do we have the mass? Do we have the velocity? So I'm going to pause it for a second. I want you guys to find me two things. I want you to find me these values, and I'm going to just make comments here, all x component and all y component. And these are backward. All y right here. And this is all x right here. And I'll just give you guys a second to get these calculators with your fantastic supercomputers in your desks. So this one, we already have it as 0, right? Because C doesn't have any x, which is why I've written all y. If we wanted to do this, if I said the sine of 90, do you remember the sine of 90? Good. So whatever this times 1 is, it's just this, right? So all we're looking for right now is just mass times y. I'm just looking for those numbers, so I'm written down. Okay, Red, do you have C or D? Okay, can you give me C? I think it's 2,000 something. I could be wrong. One more time? So how did you get it, just out of curiosity? Yeah, for C, how did you get the momentum? What did you calculate? Where'd your number come from? Oh, okay. So, all right, you're good there. I know the mass, right? 1325. What do I multiply by to get the momentum? Okay, so I don't know 1325 times 27 off the top of my head, but you guys are going to tell me. Delilah, do you have that number? Can you tell me that number?
357.
I was off by a power of 10. Okay. There's the momentum initially in the y direction. That's all from C. Okay, another big number coming up here on D. No idea what it is, but you guys can tell me. 23,000 something. 815? Okay. Now, in this problem, which is an easy problem only because this lovely right angle that they presented us with, could I put those numbers anywhere on my triangle? If you didn't catch the question, where, rather, would I put these numbers on my lovely right triangle that we sketched at the beginning? This 35,775 goes here. So we have this lovely huge side, 35,775, and this 23,815 goes right here. Everybody agree with that? Okay, now, because my final momentum winds up being the sum of these two, we have to be able to add them up. That's my initial momentum in the y, or all my initial momentum plus all my other initial momentum has to be the final. If we write this out, what was that lovely form? If we wanted to find the final, we have to take what? What's that theorem? It's Pythagorean theorem. Okay, so I could write a square here like c squared, or, and I will here, I think that I can just do this. Because everything is already at a right angle. If I want to solve for the final momentum now, I'll do what to each side? Nick says take the square root, and I love it. Okay, so here we go. Row final is apparently going to be the square root of this terrible number squared, and I'm going to make you guys all type this in for me. We're going to do it in one step, and we're going to make sure that we can all type it in the calculator correctly. So whether you have the little calculator or the big, I don't know, I'm just collecting here. You guys look. Okay. Step one, I want you to hit square root button. And I'm going to type this in the ugly way in one step, and then I'm going to write it ugly like you would type it. So you get square root and it does this. That's what your calculator says, right? Okay. Now anything inside this parenthesis is going to be inside the square root. I need to have this thing squared. Now, they're both positive in this situation, so I don't need to do anything crazy. I'm simply going to do 35,775. And then, I'm going to talk really loud next to you. Directly above the log button, or kitty corner from 7, there's a button that says x squared, right? Hit it, and it shows this up. Delilah is in the same place in the rest. By 7 for x squared. This squared. Yep, so, and that, you can use that one instead of the caret. Okay. Plus 23,815, I will hit that same x squared button and close my parenthesis, and you guys are going to give me a fairly large number, I imagine. I actually don't have it written down, and we'll see why here in a second. It's big. It should be big. After the square root. 42,976. 42,976. Okay. Just going through getting the calculation. Anybody get a different number? Okay. Awesome. We're done, right? What are we trying to find? Gosh, we need the velocity. Now, there's good news. Is there velocity hiding within my momentum? Okay. Easy part to miss right here, right now. What is traveling off at this angle in the end? One car? Both cars? What's going on? It's both cars. So, how do you find momentum just in general? It's something times something. We've already found it. How do we do it? Mass times velocity. But at the end, it's not just one car, it's both of them. So check it out. We're going to substitute for this final momentum because my two cars are stuck together. I'm going to say, all right, it's a mass of C plus the mass of D times whatever their momentum happens to be at the end. And I know that this is equal to, what was that number we just found? And I'm not going to make you repeat it, but this number. This is my final momentum. 42,976.8. And I'm going to include these units in here for this calculation just so we can see it work nicely. All right, I want one more step to solve for my velocity. What is it? Now, I'm going to divide both sides by the sum of the masses, right? The mass of the whole object. And this is going to look a little bit different because instead of writing MC plus MD, I'm actually going to plug in those values. So we had 42,976.8 in the numerator, and that's kilogram meters per second. And in the denominator, we're dividing by the mass of both of them together, which, let's see, 1325 plus 65 gets us to what? 2190 plus 1300, 4200? Somebody verify that? I think it's 4200. No, it's something 90. 4290. What am I doing? 3490, that's what I had, right? Okay, now, we don't usually show the units in here. I've elected to do it this time. We're looking for velocity, and it should be left in what unit? Angel has every answer whispered. I like it. What happens with these? And I'm in meters per second. Now, last little piece of this, almost, we're getting the velocity, the speed. I think this should come out to about 12.3, which looks like it will. 12.3? Okay, now are we done? Are we? Okay. I started this problem by saying it's really important that now we start doing what at the beginning? These guys. Okay. We are also asked for the angle, right? Okay. I have a lovely right triangle, and I know of 3 trig functions that exist that might help me find an angle. I find it natural, and it doesn't matter which way we do it. Based on the way I've drawn this, this would be the angle that I'm after, right? Are you guys cool with that's an angle theta? Now, I do want to show you, and this is going to show up in pre-calc, I drew this arbitrarily. Could I have done that one first, and then this one second, if I really wanted to? Like, it's the same thing, right? It still starts and ends at the same spot. In this situation, it would have given me this angle. Now, I don't care which angle we go with, as long as we can express our answer. Based on what we have, let's find this angle theta. Okay, for that angle theta, I have 3 sides of a triangle. And I'm going to go ahead and 42,976. 42,977, I'm just going to round it. Okay, if I want to find that angle theta and I have those 3 angles, could I use, sorry, those 3 sides, could I use sine and the inverse? Could I use cosine? Could I use tangent? As long as I have all 3 sides, I have opposite, adjacent, and hypotenuse, I'm golden. It is common to use the tangent, so let's go ahead and say, all right, tangent of theta, and gosh, tangent of theta. Lakota wisdom needed. What's tangent? And how do we remember these trig functions? SOHCAHTOA. If you don't have that locked in, get it jotted down somewhere again. SOHCAHTOA. All right, and let's look at our triangle. Tangent is TOA, which means it's what over what? What's opposite of theta? 23,815, okay? Or rho di, if you'd rather. 23,815 over, what is the adjacent to theta? $35,775. All right, big moment here. I have tangent of theta right now, but I don't want the tangent. I want it to just be theta. How do we undo a tangent? Hey, well, let's take the arctangent. So theta is exactly equal to the arctangent of 23,815 over 35,775, and it looks like this is going to be the last thing that we do. What's that theta give me? 56.348 degrees. Okay, really important. If you just tell me go 56.35 degrees, I'm going to go probably like here. It's actually pretty close to that just by happenstance. But we found this angle. We can keep this angle, I'm fine with it, but it's not in like regular from the x-axis. We start at north, we fall 56 degrees, which direction? West. East, what am I talking about? So we're going to make this a bearing. North, 56.3 degrees to the east. And check it out. We have our final velocity, it's 12.3 meters per second. And we have our lovely angle, 56.3 degrees east of north. All right, no homework tonight. Tomorrow, totally will be winning. I don't know if you guys start competing tomorrow or not. Cool. That's what we have for today. We're going to do more problems before I make you do more of these on your own. Cool. Later, Raiders.